Every electron in your body, in the sun, in the most distant star, is exactly the same. Not similar, the same, down to the limit of anything we can measure. That should be impossible, because nothing else in nature is ever perfectly identical. Not two snowflakes, not two grains of sand. And yet electrons are flawlessly alike, and that single fact is a clue that points at one of the strangest truths in all of physics. You are not made of tiny solid things. You are made of ripples in fields that fill the universe. Tonight, we will follow that clue all the way down to what those fields are doing in the dark. So dim the lights, get comfortable, and stay with me, because the answer hides inside the emptiness itself. Part 1. The little ball that was never there. I want to start tonight with a small confession, and it might be the most freeing thing you hear all week. Almost everything you were taught about what the world is made of is quietly, gently wrong. Not wrong in the way a wrong answer on a test is wrong, where you simply swap it for the right one and move on. Wrong in a way that goes underneath the answers, into the picture you carry in your head without ever choosing it. You were handed an image of matter when you were very young, and you have been seeing the universe through that image ever since. The image goes something like this. Matter is made of atoms, and atoms are tiny solar systems, with a little nucleus in the middle and tinier electrons whizzing around it like planets. Zoom in further, and you find particles, little balls of stuff, hard and definite, like impossibly small marbles. Everything you can touch, the chair beneath you, the warmth of a blanket, your own hand resting on the pillow, is supposedly built from these little balls, packed and bonded and arranged into the shapes of the world. It is a tidy picture. It is easy to draw. And it is not what physics actually says is going on. Here is the strange truth that took the smartest people of the 20th century decades to accept. There are no little balls. There never were. When you go all the way down, past the molecules and the atoms and the nucleus, you do not find smaller and smaller marbles. You find something that does not behave like a thing at all. You find fields, continuous, invisible fields that fill all of space, every corner of it, with no gaps anywhere. And every particle you have ever heard of, every electron and quark and photon, is not a ball sitting in space. It is a ripple, a vibration, a little disturbance moving through a field that was already there. That is the shift I want to walk you through tonight, slowly, the way you would walk through a quiet house in the dark, letting your eyes adjust until the shapes resolve. Because once you make this shift, once you genuinely understand what a quantum field is, the universe stops looking like a box of objects and starts looking like something far stranger, and I think far more beautiful. And the title I have given this is a promise. I am going to show you that the field, once you understand it, never stops doing something. It is never still. It is never silent. Even in the places you would swear are empty, even in perfect darkness, even where there is, by every ordinary definition, nothing at all, the field is busy. By the time we are done, you may find that empty space is the most active thing in the entire universe. You do not need any mathematics for this. I promise you that. This is not a lecture, and there will be no equations to memorize. What we are doing is more like learning to see one of those images that looks like random noise until someone tells you what is hidden inside, and then you can never not see it again. The change happens in you, not on a page. So all I ask is that, for the next couple of hours, you loosen your grip on the marble. Let the little ball go. We are going to build a better picture together, piece by piece, and I think you are going to like where it leaves you. Let me give you something to hold on to right at the start, because the rest of the night is going to lean on it. Consider the electrons in your own body. There are an unimaginable number of them, threaded through every cell, every atom, holding your chemistry together as you lie there breathing. Now consider the electrons in the Sun, 93 million miles away, in that roaring furnace of light. And the electrons in a star on the far side of the galaxy, so distant that the light leaving it tonight will not reach Earth for tens of thousands of years. Here is the thing that should stop you for a moment. Every single one of those electrons is, in the most literal sense, physics can manage. The same. Not similar, not nearly identical. The same. They have exactly the same mass, exactly the same charge, exactly the same properties, down to the limit of anything we can measure. And that is not a coincidence. It is a clue, maybe the biggest clue of all, and it points directly at the idea that there are not countless little electron balls scattered across the cosmos. There is one electron field, spread across everything, and every electron is the same kind of ripple in that one field. We will come back to that clue and unfold it properly, because it is one of the most quietly mind-altering facts in all of science. But I wanted you to have it now, like a small stone in your pocket, so you can feel the weight of where we are going. The world is not made of things, it is made of fields. And the fields are doing something right now, in this room, in the space between your body and the ceiling, in the dark behind your closed eyes. I want to be honest with you about why this picture is so hard to hold on to, because the difficulty is not a failure on your part. It is built into how we evolved and how we live. Our brains were shaped by a world of rocks and rivers and animals, things with edges, things you could pick up or run from. The little ball is the natural way a creature like us imagines anything small, because everything we ever handled had a surface and a weight and a place. The field, by contrast, is something our senses never had any reason to perceive. We feel its consequences constantly, in light and heat and solidity, but we never feel the field itself, the way a fish, I suspect, never feels the water it has always swum in. So when I ask you to trade the marble for the ripple, I am asking you to override millions of years of instinct, and that is genuinely hard, and it is fine if it takes the whole night to settle in. The point is not to force it. The point is to let the new picture sit beside the old one until gradually it starts to feel more true. There is something worth saying about why this matters beyond the wonder of it, why it is not just a clever reframing for its own sake. The field picture is not one possible story among many that we could take or leave. It is the foundation of essentially all of modern physics. The framework underneath the laser in a checkout scanner, the imaging in a hospital scanner, the chips inside the device that might be playing you these words. Every one of those technologies was designed by people thinking in terms of fields and their excitations, not little balls. So the strange idea I am handing you tonight is not a fringe speculation. It is the working picture of reality used by the people who built the modern world. They just rarely stop to mention how deeply odd it is. We are going to stop and notice. So how on earth did anyone ever figure this out? How do you go from a universe that looks, for all the world, like it is made of solid objects, to the claim that solidity itself is a kind of illusion stitched together from vibrations in invisible fields? That story does not begin in a particle accelerator or a chalkboard full of symbols. It begins, of all places, with a bookbinder's apprentice who could barely do algebra, standing in a basement, sprinkling iron filings around a magnet, and watching them arrange themselves into a pattern that no one could quite explain. If the world is not made of things, then what is it made of? And how did a man who never learned the mathematics come to see it first? Is less than break time equals 1s is greater than. Part 2. How we accidentally discovered that the world is made of fields. The man in the basement was Michael Faraday, and he is one of my favourite people in the whole history of science, partly because he arrived at one of the most important ideas humans have ever had almost by feel. Faraday had very little formal education. He came up as an apprentice to a bookbinder, which meant he was surrounded by books he could read in his spare moments, and he read them hungrily. He had almost no training in mathematics, which in his day was supposed to be the gatekeeper of serious physics. And yet he had something rarer, a kind of physical intuition so strong that he could practically see forces that no one else could picture. When Faraday scattered iron filings on a card held above a magnet, the filings did not lie there randomly. They lined up into graceful curving arcs, looping from one end of the magnet to the other, tracing out a pattern in the empty air around it. Anyone could see the pattern. The question was what it meant. Most people at the time would have said that the magnet simply reaches out and pulls on the iron, action at a distance, one object tugging another across a gap of nothing. But Faraday looked at those curving lines and had a different thought, a thought that turned out to be one of the most consequential in the history of the world. What if the lines are not just a picture of where the iron ended up? What if the lines are real? What if the space around the magnet is genuinely filled with something, an invisible influence reaching into every point, and the filings are simply revealing a structure that was there all along? That's something he called a field. The space around the magnet, in Faraday's mind, was not empty. It was filled with a magnetic field, a real physical presence at every point, ready to push or pull on anything that could feel it. And the same went for electric charges and for gravity. The world, in this picture, was not a collection of objects sitting in a void, reaching across the emptiness to grab one another. It was a place where space itself carried fields, and objects responded to the field right where they sat. The emptiness was not empty. It had properties. That was the first crack in the marble, and it was opened by a man who could not have written down the equations to save his life. The equations came later, from someone who could. James Clerk Maxwell was, in many ways, Faraday's opposite, a mathematician of the first rank who took the older man's pictures and intuitions and translated them into precise mathematical law. And when Maxwell finished writing down the rules that governed electric and magnetic fields, something fell out of the mathematics that no one had asked for and no one expected. The equations said that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So, in principle, you could have a ripple that sustained itself, an electric field giving rise to a magnetic one, the magnetic one giving rise back to an electric one, the whole thing leapfrogging through space without needing anything to carry it. A self-sustaining wave in the field itself. Maxwell could even calculate how fast such a wave would travel, straight from the constants in his equations. And when he worked out the number, it came out to about 186,000 miles per second. That number was already famous. It was the measured speed of light. The conclusion was unavoidable and, to my mind, one of the most thrilling moments in all of science. Light is not a separate mysterious substance. Light is a ripple in the electromagnetic field, a wave of the field shaking itself, rolling through space at the only speed such a wave can go. The light from your bedside lamp, the light from the stars, the warmth of sunshine on your skin, all of it is the field vibrating. Sit with what that did to the idea of empty space. Before Faraday and Maxwell, space was just the stage, the inert nothing in which the real action of objects took place. After them, space had become a participant. Empty space could carry waves. It could store energy. It could transmit forces. The container had turned out to have a life of its own, and this was still before anyone knew anything about quantum mechanics. This was the classical field, smooth and continuous, and already it was enough to overturn the idea that the world is just things in a void. But then, at the turn of the 20th century, a problem appeared, and it is the problem that cracks the door open into everything we are going to talk about tonight. Quantum mechanics arrived, and it brought with it a deeply strange discovery. Energy, in many situations, does not come in a smooth, continuous stream. It comes in lumps. Max Planck found that hot objects give off light only in discrete packets of energy. Albert Einstein took that idea further and proposed that light itself, when it interacts with matter, behaves as though it arrives in indivisible chunks, which we now call photons. So here was the tension, and it was a real one. Maxwell's field was perfectly smooth, a continuous wave that could carry any amount of energy you liked. But the new physics insisted that, when you actually measured light, it came in countable lumps. How can light be a smooth wave in a field and also a stream of discrete packets at the same time? Which one is the truth? The resolution came in the late 1920s, and it is the true birth of the idea at the center of tonight's journey. A handful of physicists, including Paul Dirac, Max Born, Pascual Jordan, Werner Heisenberg, and Wolfgang Pauli, took a radical step. Instead of treating the field as a smooth classical thing, they applied the rules of quantum mechanics to the field itself. They quantized it. Picture the electromagnetic field as an enormous collection of tiny springs, one at every point in space, all able to vibrate. In the old classical picture, each spring could jiggle by any amount, smoothly, continuously. In the new quantum picture, each spring could only vibrate in discrete steps. 1 unit of energy, 2 units, 3 units, never 1.5. And when you add exactly 1 unit of vibration to the electromagnetic field, what you get, popping out of the mathematics, is a photon. Stop and notice what just happened, because it is the whole game. The photon was not added to the theory by hand. Nobody said, "Let us put a particle of light into our equations." The particle appeared all on its own, as the smallest possible vibration of the field. The field came first. The particle is what the field looks like when you give it 1 quantum of energy. And that reframes the entire universe in a single move. The fundamental object is the field, spread across all of space. The particle, the thing we used to imagine as a little ball, is secondary. It is a ripple, a quantum of disturbance, an excitation of the field that was already everywhere. I want to linger on the spring image for a moment, because it is the closest thing we have to a feel for what a quantum field is, and it rewards a slow look. Imagine all of space filled with an unbroken grid of tiny springs, one at every point, each connected to its neighbors, so that when one jiggles, the motion spreads to the ones beside it. In the classical world of Maxwell, each spring could be displaced by any amount, and the motion would ripple smoothly across the grid as a wave. That smooth wave is light in the old picture. Now add the quantum rule, the rule that each spring can only carry whole units of vibrational energy, never a fraction. Suddenly, the smooth wave has to be built out of countable lumps. A dim beam of light is not a faint, continuous wave anymore. It is a small number of these lumps, these quanta, travelling through the grid. A bright beam is a great many of them. The lumps are photons, and they are not objects laid on top of the grid. They are the grid's allowed units of trembling. That single mental image, an infinite grid of springs that can only shake in whole steps, is most of quantum field theory in a picture. It is worth pausing on how reluctant even the great physicists were to take this seriously, because it tells you how counterintuitive it is. Einstein himself, who proposed the photon, spent years uneasy about what it really meant, and never fully made peace with the quantum world he had helped to start. The people building these ideas were not handed them on a silver platter. They argued, they doubted, they resisted, and they were dragged toward the field picture by the sheer weight of the experiments, which kept insisting on results that only made sense if light and matter were lumps of an underlying continuous field. That reluctance is a comfort in a way. If the founders found it strange, you are in excellent company finding it strange too. The universe simply does not run on the intuitions we were born with, and learning that is part of the wonder. This is the moment the marble lost. We have been living in a field universe ever since, even though almost nobody outside of physics talks about it that way. The picture you carry in your head, the one with the little balls, is a leftover from before this discovery, a ghost of an older idea that the science quietly replaced and then forgot to tell everyone about. The world is fields. Particles are ripples. And if that is true for light, if the photon is just a ripple in the electromagnetic field, then a question rises up almost on its own, and it is the question that opens the next part of our night. If light is a ripple in the light field, then what is an electron a ripple in, and just how many fields does it take to build an entire universe? Is less than break time equals 1s, is greater than, part 3, everything is a ripple, the one field idea. Let me make sure we have the word field firmly in hand, because the whole night rests on it, and it is simpler than it sounds. A field, in physics, is just a quantity that has a value at every point in space. You already live with fields all the time without calling them that. Think of the temperature in the room around you. At every point, near the window, by the door, just above your bed, the air has some temperature, a number. That collection of numbers, spread smoothly through the whole room, is a field. The temperature field. Or think of the air pressure across a continent on a weather map, higher here, lower there, varying from place to place. That is a field too. A field is nothing more exotic than this. A value at every point, everywhere. Now take that idea and make it the foundation of reality. Quantum field theory says that underneath everything there are fields like this, but for the fundamental ingredients of the universe. Spread across all of space, filling every point with no gaps, there is an electron field. It is invisible, it has no temperature or pressure, but it is there, the same way the temperature field is there, a quantity with a value at every point. And here is the part that takes some getting used to. An electron is not a separate object dropped into that field. An electron is a ripple in the field, a self-contained little vibration, a knot of disturbance, travelling through the electron field the way a wave travels across the surface of a pond. The field is the water. The electron is the wave. And it is not just electrons. There is a photon field, and photons are ripples in it. There are quark fields, and the quarks inside every proton and neutron in your body are ripples in those. When you tally up all the fundamental fields that the best theory we have, the standard model, requires, you get around 17 of them, layered over the same space, like transparent sheets stacked on top of one another, each one filling all of reality, each one capable of carrying its own kind of ripple. Everything you have ever seen or touched or been is some combination of vibrations in those 17 or so fields. The whole material world, reduced to a small number of invisible oceans and the waves that move across them. Now I can finally pay off the clue I gave you at the very beginning, the small stone in your pocket. Remember the strangeness of identical electrons. Every electron in the universe has precisely the same mass and precisely the same charge, to the limit of measurement, no exceptions ever found. This is genuinely bizarre if you think about it through the old picture. Look around at the ordinary world. No two snowflakes are exactly alike. No two grains of sand are identical. No two stars. No two trees. No two faces. Everything that is made of many parts comes in endless variation, because there are countless ways to arrange the parts. So if electrons were tiny manufactured balls, you would expect them to vary too, even slightly. One a touch heavier, one a touch more charged, scratches and dents from a long life in the cosmos. But they do not vary. They are flawlessly, eerily the same. The field picture explains this instantly, and the explanation is so clean it feels like a magic trick. Electrons are all exactly alike because they are not separate objects at all. They are the same single field, vibrating in the same way in different places. There is one electron field, and an electron here in your hand and an electron in a distant galaxy are the same kind of ripple in that one underlying thing. Of course they are identical. They are made of the same field, vibrating according to the same rules. It would be more shocking if they were different. Asking why all electrons are the same is like asking why all the waves on a single pond are made of the same water. There is only one pond. Let me push the pond image a little further, because it helps. Picture a perfectly still pond at night, the surface like glass. That stillness is the field at rest, what we might loosely call empty. Now drop a pebble, and a ring spreads out, a moving pattern of the water rising and falling. That ring is a particle. It has a location, it carries energy, it moves, and yet it is not a separate object sitting on top of the water. It is the water doing something. You could never scoop the ring out and hold it apart from the pond, because there is nothing to it but the pond in motion. That is what a particle is, not a thing on the field. The field, locally excited. And this is the first place where understanding the field genuinely changes what you see when you look at the world. Under the old picture, your body is a collection of tiny solid objects, marbles packed into the shape of you. Under the field picture, your body is a pattern, an arrangement of standing ripples in a handful of fields that fill the entire universe. The substance you thought you were made of melts into something more like music, a set of vibrations holding a shape for a while. You are not stuff in space. You are space doing something. I will let you sit with that one, because it is the kind of idea that rewards a slow breath. The old picture and the new one really do feel different in the hand, and the contrast is worth dwelling on. A marble can be chipped. It can be scratched, worn down, made slightly lighter by a long tumble in a river marked by its particular history. A marble is an individual, with its own dents and scars. A ripple in a field cannot be an individual in that way. It cannot be slightly heavier than the standard, because its properties are set entirely by the field it lives in, not by any private history of its own. There is no inside to it, no hidden machinery, no little extra weight tucked away. It is the field, expressing itself the only way the field can. That is why the particles of the universe come in such a small number of perfectly standardized types. They are not manufactured objects. They are the standing patterns that a small set of fields are allowed to make. How do these ripples interact, then, if they are all just disturbances in their own fields? Here the picture stays consistent, and it is rather elegant. Fields can overlap, and when they do, they can pass ripples back and forth. Two electrons repel each other not because two little balls bump, but because their fields are coupled to the electromagnetic field, and they exchange a ripple of it, a photon passed between them like a quiet message. The forces of nature, in this view, are fields talking to fields, trading vibrations. Even the push you feel when you press your hand against the bed is, at the lowest level, fields refusing to overlap, ripples in the electron fields of your hand, and the mattress declining to occupy the same arrangement. Solidity is a negotiation between fields. There is no marble anywhere in it. Let me give you one more number to feel the scale of this, because the sheer reach of the idea is part of its strangeness. In the observable universe, the part we can in principle see, there are something on the order of 10 to the 80th power electrons. That is a 1 followed by 80 zeros, a number so large that there is nothing in ordinary life to compare it to. And field theory says that every one of those, all 10 to the 80th of them, is the same ripple in the same single field. It is, in a sense, one object, expressed an unthinkable number of times across all of space. The universe is not crowded with countless different electrons. It is one electron field, ringing in 10 to the 80th places at once. Let me dwell a little longer on the identical electron clue, because the more you turn it over, the more remarkable it becomes, and it is one of those facts that quietly changes how you see your own body. Every chemical reaction that keeps you alive, every signal firing in your brain as you listen, depends on the fact that electrons are perfectly interchangeable. If electrons varied even slightly from one to the next, chemistry as we know it would not work, because the rules that govern how atoms bond rely on electrons being identical indistinguishable, swappable, without consequence. Life itself leans on the one-field idea. The reason carbon behaves the same way in your cells as it does in a diamond or a distant comet is that the electrons doing the bonding are, everywhere, the same ripple in the same field. You are built on a sameness that runs through the whole universe. There is a subtlety here that physicists treat with great care, and it is worth touching gently because it deepens the strangeness. When two electrons come close, you cannot even keep track of which one is which. They are not just identical in their properties. They are genuinely indistinguishable, to the point where swapping them changes nothing about the world, and the mathematics of quantum theory has to be built to respect that. This is not a limitation of our instruments, a failure to look closely enough. It is a basic feature of reality. There is no hidden label on an electron, no serial number, no individual identity, because there is no individual object there to carry one. There is only the field, vibrating in two places, and the two ripples are as interchangeable as two identical notes played on the same string. The world, at its base, is made of patterns without personal histories. There is one more consequence of the one-field idea that I find quietly beautiful, and it concerns how particles can be created and destroyed at all. In the old marble picture, it is mysterious that a particle can simply come into being from energy or vanish into it, because where does a solid little ball go when it disappears? But in the field picture, creation and destruction are the most natural things in the world. To make a particle, you add a quantum of energy to its field, and a ripple appears. To destroy one, you remove that quantum, and the ripple smooths back into the field. Nothing has to be conjured from true nothing, or annihilated into true nothing. The field is always there, and particles are just the field rising and falling. When a star converts matter into light, when a particle collision produces a spray of new particles, what you are watching is energy being poured into various fields and ripples, forming in response. The stuff of the world is endlessly being made and unmade, and the fields are the constant beneath all that change. There is a gentle way to feel the truth of the one-field idea in your own experience, and I offer it because it makes the abstraction personal. The next time you switch on a light, consider that the brightness flooding the room is countless ripples in a single field, the same field that carries starlight across the universe and the warmth of the sun to your skin. The next time you feel the solidity of something firm beneath your hand, consider that you are feeling electron fields declining to overlap, ripples politely refusing to share the same space. You do not have to do anything special to be surrounded by the fields. You already are, always, in every moment. They are not exotic things locked away in laboratories. They are the light in your room, the warmth on your face, the firmness of the ground, the substance of your own body, all of it the same small set of fields, doing what they do. So, the picture is coming into focus. Reality is not a box of separate things. It is a set of overlapping fields, filling everything, and particles are the ripples those fields are allowed to make. But I have been a little too gentle so far. I have let you keep imagining the ripple as a small, soft blob, a fuzzy little wave packet that is at least sort of like a tiny object. The truth is stranger than that, and it leads us straight into one of the most unsettling facts in physics. If the electron is just a ripple, with no marble hiding underneath, then how big is it? Where is its edge? And what happens when the very best experiments in the world try to find the surface of a thing that may not have one at all? Is less than break time equals 1s is greater than part 4. The electron has no size, and antimatter fell out of an equation. Here is the fact that I think breaks the marble for good, the one that finally makes it impossible to keep the little ball in your mind. As far as every experiment ever performed can tell, the electron has no size at all. It is not a small ball. It is not even a very, very small ball. It is, to the limit of everything we can measure, a point. A ripple with no marble at the center, an excitation of the field that has no internal structure, no surface, no edge to find. We have looked and looked hard with the most powerful instruments humanity has ever built, and we have never found any sign that the electron is anything other than a true point. I should be careful about what point means here, because it sounds like a contradiction. How can a thing be real, carry charge, carry mass, do all the work an electron does, and yet have no size? The answer is that the size you instinctively want to give it is not the size of a solid object. When physicists talk about the extent of an electron, what they really mean is how spread out the field's excitation is and how far its influence reaches, not the radius of some little sphere. The electron has presence, it has effects that reach out through the fields around it, but it has no body in the way a marble has a body. The instinct to picture a tiny hard sphere is exactly the instinct the field picture asks you to give up. There is nothing solid in the middle. There is only the field doing something in a region without a definite boundary. This is hard to accept, and I do not blame anyone for resisting it, because everything in our daily lives trains us to expect that small things are just smaller versions of big things. A grain of sand is a tiny rock. A speck of dust is a tinier speck still. So surely an electron is just a really, really tiny ball. But nature does not honor that expectation at the bottom. When you go down far enough, the smaller versions of things stop being things and become excitations of fields, and an excitation does not need a surface. Every attempt to find substructure inside the electron, to discover that it is secretly made of smaller pieces, has come up empty. As best we can tell, you have reached the floor. There is the field, and there is the ripple, and there is nothing more solid underneath. Now, I want to tell you a story that shows just how powerful this field way of thinking turned out to be, because it produced one of the most astonishing predictions in the history of science, and it did it almost by accident, out of pure mathematical consistency. The story belongs to Paul Dirac, one of the strangest and most brilliant minds the field has ever known, a man so quiet and literal that the people around him used to joke that a Dirac was a unit of one word spoken per hour. In 1928, Dirac was trying to do something that sounds modest, and was in fact enormously hard. He wanted to write down an equation for the electron that obeyed both of the great theories of his time at once, quantum mechanics and Einstein's relativity. Quantum mechanics governed the small, relativity governed the fast. The electron is both small and fast, so it needed an equation that respected both, and nobody had managed to write one that worked. Dirac found his equation, and it was beautiful, and it described the electron with remarkable success. But it had a feature that looked, at first, like a serious flaw. The mathematics insisted on extra solutions that seemed to describe particles with negative energy, which made no physical sense. You cannot have a particle with less than nothing of energy. Most people would have shrugged the extra solutions off as mathematical garbage, an artifact to be ignored. Dirac did something braver. He took the mathematics seriously. He asked what it would mean if those solutions were not garbage, but were pointing at something real that simply had not been seen yet. His answer, after some wrestling, was extraordinary. The equation, he realized, was demanding the existence of a mirror twin to the electron, a particle with exactly the same mass but the opposite electric charge. Where the electron is negative, this twin would be positive. It would be, in every other respect, the electron's perfect reflection. Dirac had, on paper, with nothing but the requirement that the mathematics be consistent, predicted antimatter. He called this twin the positron, and at the time he proposed it, not a single one had ever been observed. He was telling the world that an entire category of matter must exist, the opposite of the matter we know, purely because the equation refused to be consistent without it. And then, in 1932, just a few years later, A physicist named Carl Anderson, studying the showers of particles that rain down on Earth from space, found it. In his detector, he saw the track of a particle with the mass of an electron but curving the wrong way in a magnetic field, which is exactly what a positively charged electron would do. The positron was real. Antimatter was real. The field theory had reached out into the unknown and conjured a new piece of reality from sheer mathematical necessity, and the universe had obligingly produced it. I find it hard to overstate how strange and wonderful that is. A man sat at a desk, insisted that his equation make sense, and in doing so discovered half of the matter content of the cosmos before anyone had laid eyes on it. The lesson generalized quickly. Every kind of particle, it turns out, has an antiparticle, a mirror twin of opposite charge, and the field picture explains why with no extra effort. The fields come with this symmetry built into their structure. Matter and antimatter are simply two kinds of ripple that the same fields are allowed to make, two ways the field can vibrate, related to each other like a wave and its reflection. When a particle meets its antiparticle, the two ripples cancel, the disturbances undo each other, and their energy is released, usually as photons, ripples in the light field. They do not so much destroy each other as smooth back out into the field they came from. Why does all of this matter for the thread we are following tonight? Because it tells you something crucial about how seriously to take the field picture. This is not a loose metaphor, a pretty way of talking that we could swap for another if we felt like it. The field picture is predictive enough to discover whole new forms of matter from consistency alone. It found antimatter before we looked. And that track record is exactly why, when the same theory tells us something deeply counterintuitive about empty space, about what the fields are doing when there is supposedly nothing there, we cannot simply wave it away as a manner of speaking. A theory that predicts antimatter from an equation has earned the right to tell us that nothing is full. It is worth pausing on how strange Dirac's method was, because it represents a way of doing science that still astonishes me. He did not start from a pile of puzzling data about antimatter and reason his way to an explanation, the way we usually imagine discovery working. He started from the demand that two theories be made consistent with each other, followed the mathematics where it insisted on going, and trusted it even when it pointed at something absurd. The universe, it turned out, was obeying the mathematics more faithfully than anyone had dared to hope. This has happened again and again in the physics of fields, where an equation, taken seriously, predicts something no one expected, and the prediction comes true. It suggests that the fields are not just a convenient description we invented, but something the universe genuinely runs on, deeply enough that its own internal logic can be read off the page before it is ever seen in an experiment. When the mathematics of fields speaks, reality has a habit of listening. There is a quieter unease that this part should leave you with, and I want to name it before we move on. If the mathematics of the fields demanded antimatter, a thing we had never seen, then it is fair to wonder what else the fields are doing that we have not thought to look for. What other behavior is folded into those equations, waiting, that our intuition would never expect? Dirac is buried in the Abbey at Westminster, and engraved in the stone near his memorial is his equation, a single line of mathematics that found a hidden half of the universe. It is a good reminder that the fields know things we do not, and that they have been right before, even when they sounded absurd. I want to sit with the no-size idea a little longer, because it is the kind of fact that can quietly rearrange your sense of what you are. Think about what it means for the matter in your body. The protons and neutrons in your atoms do have a size, a tiny extent, but they are themselves made of quarks, and the quarks, like the electron, appear to be sizeless points, ripples with no marble at the center. The electrons that surround every atom are sizeless points too. So when you ask what your body is actually made of, at the very bottom, the honest answer is that it is made of sizeless excitations of fields, arranged into patterns, held together by forces that are themselves the trading of ripples. The overwhelming majority of what you call solid is the empty room between these point excitations, room that is not really empty at all, because it is full of the fields. You are, in a very literal sense, mostly field and almost no stuff. There is a question this raises that physicists have wrestled with for a long time, and it is worth naming because it shows the limits of even the field picture. If the electron is a true point, then some of its properties, when you calculate them naively, threaten to become infinite because you are concentrating things into zero size. The early builders of quantum electrodynamics had to develop careful techniques to handle these infinities, a process that troubled even Feynman, who once called it a kind of sweeping under the rug, even though it gave answers that matched reality to astonishing precision. That tension has never fully gone away, and it is one of the reasons some physicists suspect that the point particle, the sizeless ripple, may itself be an approximation of something deeper still, perhaps a tiny vibrating string or some structure we have not yet grasped. The field picture is the best we have, and it is extraordinarily good, but even it carries hints that the story is not finished. I find that honest uncertainty more wonderful than any false tidiness would be. So, if a field can predict particles we had never seen, the natural next question is how precisely it can predict the ones we can see. When we point the full machinery of quantum field theory at something we can actually measure in the laboratory, just how good is the agreement? Is it good in the loose way, that most of science is good, right to within a few %? Or is it good in some far more frightening way? Because the answer turns out to be the single most precise agreement between theory and reality that human beings have ever achieved, and the way that precision is built is going to lead us straight to the restless emptiness at the center of tonight's story. Is less than break time equals 1s? Is greater than? Part 5. The most accurate prediction humans have ever made. The theory that handles the electron and the photon fields together in their full quantum glory is called quantum electrodynamics, which is a mouthful, so almost everyone just calls it QED. It was put together in the 1940s, in the years right after the Second World War, by a small group of physicists working partly in parallel and partly in competition. The names worth knowing are Richard Feynman, Julian Schwinger, Sine, Itiro Tomonaga, and Freeman Dyson. Feynman is the famous one, the bongo-playing, safe-cracking, storytelling character who became the public face of physics for a generation. Schwinger and Tomonaga did the heavy mathematical lifting along different roads to the same place, and Dyson was the one who proved that the different approaches were secretly the same theory, stitching the whole thing into a single coherent structure. Together they produced what is, by a wide margin, the most successful physical theory ever written. Let me show you what successful means here, because the number is genuinely difficult to believe. The electron, besides having charge and mass, behaves like a tiny magnet. It has a magnetic strength, a measure of how strongly it responds when you put it in a magnetic field. QED lets you calculate that magnetic strength from first principles, from the theory of the electron and photon fields alone. And when you compare the calculated value to the measured value, the one we get from real experiments on real electrons, the two agree to about 12 decimal places. 12. That is agreement of roughly 1 part in a trillion. I want to make that number something you can feel, because written down as a decimal, it just looks like a long string of digits, and the wonder leaks out of it. Imagine measuring the distance from New York to Los Angeles, around 2,400 miles across the continent. Now imagine making that measurement so precisely that your error, your uncertainty, is less than the width of a single human hair. That is the kind of agreement we are talking about between the QED prediction for the electron's magnetism and the value nature actually shows us. It is not science being roughly right. It is the closest thing to perfect correspondence between a human idea and physical reality that has ever been demonstrated. We wrote down what the field should do, and the universe agreed to a part in a trillion. But here is the part that turns this from an impressive piece of trivia into something that belongs at the center of our story tonight. Why is the calculation so precise, and what does the calculation actually contain? When physicists compute the electron's magnetism, they do not just consider a lone electron sitting by itself. They cannot, because there is no such thing as a lone electron sitting by itself. Every electron is constantly interacting with the fields around it, including the restless activity of empty space. The calculation has to include the electron emitting and reabsorbing photons, the electron being surrounded by a fleeting cloud of particle pairs that flicker into being and vanish, the whole busy commerce between the electron and the supposedly empty space it sits in. The famous precision of QED is precision about a process that is anything but quiet. The number works because the calculation faithfully accounts for what the field is doing, even where there is nothing. Let me introduce you to a heavier, louder cousin of the electron, because it is right at the frontier of all this, and it has been in the news. The muon is, in almost every way, just a fatter electron. Same charge, same basic behavior, but around 200 times the mass, and unstable, decaying away in a fraction of a second. Because it is so much heavier, the muon is more sensitive to the activity of the fields around it. Its little internal magnet is, in a sense, listening more carefully to every whisper from every field in nature, including fields we might not yet know about. So physicists built an experiment to measure the muon's magnetism with extreme care, hoping that any disagreement with the prediction might reveal a hint of new physics, some field beyond the ones in our current theory making itself felt. That experiment, called Muon G-2, ran at Fermilab outside Chicago, and it released its final and most precise results in 2025. The way it works is poetic when you understand the field picture. The muons are sent racing around a ring, and as they go, they spin, and that spin wobbles, precesses, at a rate set by the muon's magnetism. And the muon's magnetism, just like the electrons, is shaped by every field whispering to it as it flies. So the wobble of the muon in that ring is, quite literally, a readout of what the quantum fields are doing in the space the muon passes through. We are watching the activity of empty space, written in the precession of a tiny spinning ripple. For years, there was real drama here, and I want to be honest with you about where it stands, because this is live science, not a settled story. The measured wobble of the muon seemed, for a long while, to disagree slightly with the value predicted by the Standard Model, our current best theory. Not by much, but by enough to make physicists' pulses quicken, because a genuine disagreement would mean there is a field out there we have not yet discovered, tugging on the muon. Then, through 2024 and 2025, improved calculations of the Standard Model prediction, done with enormous supercomputer simulations of the relevant fields, shifted the predicted value closer to the measurement, narrowing what had looked like a crack. As of now, whether a true discrepancy survives is still genuinely argued among the experts. It may yet reveal something new. It may quietly close. We do not know. But notice the size of the argument, because that is the point I want you to carry forward. Even our deepest uncertainty here, even the gap we are not sure is real, lives down at the level of 1 part in a billion or so. The field picture is right to a degree that is almost absurd, so right that physicists get excited about a possible disagreement in the 10th or 11th decimal place. When a theory is confirmed to that precision, again and again, you cannot dismiss what it tells you, even when what it tells you is strange. And it is about to tell us something very strange indeed. We are standing, on the most thoroughly tested theory in the history of human thought. And that theory is built, at its foundation, on the idea that empty space is never empty. Let me give you a way to picture how these calculations actually work, because it makes the connection to the restless vacuum vivid, and it is one of Feynman's great gifts to the world. Feynman invented a way of drawing these interactions, little sketches we now call Feynman diagrams, in which an electron travels along as a line, and at various points it can emit a photon which travels a while and is reabsorbed, or it can momentarily produce a pair of virtual particles that quickly vanish. Each possible drawing represents one way the process can happen, one contribution to the final answer. To calculate the electron's magnetism precisely, you add up the contributions from more and more elaborate diagrams, with more and more loops of virtual particles flickering in and out. The simplest diagram gives you a rough answer. Adding the next layer of diagrams, the ones with a single loop of virtual activity, refines it. Adding still more refines it further. And here is the point that ties to our thread. Those loops are the vacuum. They are the electron interacting with the restless flickering of empty space. The legendary precision of the answer comes precisely from carefully counting up everything the field is doing around the electron, including in the supposed nothing. I want to underline just how unusual this situation is in the broader story of science, because we have grown so used to it that we forget to be amazed. In most of human knowledge, theory and measurement agree to within a few %, and we call that a triumph. In some fields, agreeing to within a factor of 2 is cause for celebration. But here, in quantum electrodynamics, we are talking about agreement to 10, 11, 12 decimal places, sustained across decades of ever more careful experiments. No other theory in any science comes close. It is as if you described the rules of a game in the abstract and then found that the universe had been playing exactly that game flawlessly since before there were stars. When a theory reaches that level of confirmation, it stops being merely a useful model and starts being something we have to take seriously as a description of how reality is actually put together. And what this particular theory says, underneath all its precision, is that the electron is a ripple in a field, surrounded by a vacuum that is anything but empty. It is worth dwelling for a moment on what this precision means for the question at the center of our night, because it is easy to admire the number and miss the point. The reason we can trust what quantum field theory tells us about empty space, about the restless, flickering vacuum we are building toward, is precisely this track record. A theory that agrees with reality to 12 decimal places has earned an extraordinary level of trust, the kind of trust that obliges us to take its stranger claims seriously rather than dismissing them as figures of speech. When such a theory tells us that the vacuum is full, that empty space is doing something, we are not free to shrug. The same mathematics that gets the electron's magnetism right to a part in a trillion is the mathematics that insists the nothing is alive. You cannot keep one and discard the other. They are the same theory, confirmed by the same relentless agreement with the world. There is a human dimension to this story that I find moving, and it is worth a moment. Tomonaga did much of his work in Japan, during and just after the devastation of the war, in difficult conditions, isolated from the physicists working on the same problems in America. Schwinger built his version of the theory in a formidably mathematical tower of his own. Feynman built his with pictures and intuition, almost a different language, and it was Dyson, a young man, who saw that these very different-looking approaches were secretly one and the same theory, and translated between them. 3 roads up the same mountain, found independently, on opposite sides of a planet still smouldering from war, all arriving at the same summit, the same description of the electron and its restless surrounding field. The universe gave the same answer to everyone who asked carefully enough, which is, when you think about it, one of the quiet miracles of science. So let me ask the question, that every one of these ultra-precise measurements has been quietly leaning on the whole time. Each of them, the electron's magnetism, the muon's wobble, only works because the vacuum, the so-called nothing, is doing something. The calculations demand it. The agreement with reality confirms it. So what, exactly, is the field doing when there is supposedly nothing there at all? What happens in a box from which you have removed every particle, every speck of light, and cooled it to the coldest temperature allowed by the laws of physics? If the marble picture were right, the answer would be simple. Nothing happens because there is nothing there. But the field picture gives a different answer, and it is the answer that gives this whole night its title. Is less than break time equals 1s. Is greater than... Part 6. The vacuum is not empty. We arrive now at the turn that gives tonight its name, and it follows directly from where we just stood. The precision of quantum electrodynamics only works because empty space is doing something, so let us finally look squarely at what that something is. Let us go to the emptiest place we can possibly imagine and ask what is happening there. Take a box. Pump out all the air, every last molecule, then pump out the light, every photon, until it is perfectly dark inside. Then cool the box to absolute zero, the lowest temperature the laws of physics allow, the temperature at which ordinary motion stops. Shield it from everything outside. By every definition you grew up with, that box now contains nothing. It is pure, perfect emptiness. And yet, according to quantum field theory, the fields inside that box cannot hold still. They are trembling right now, with an energy that can never be removed. The reason they cannot hold still comes from one of the bedrock rules of quantum mechanics, the uncertainty principle, and I can give it to you without any mathematics. The uncertainty principle says, in plain terms, that certain pairs of properties cannot both be exactly fixed at the same time. For a field, this means you cannot have the field sitting at exactly zero with exactly zero rate of change, both perfectly definite, both perfectly still. That combination, total stillness and total certainty, is forbidden. The field is not allowed to be perfectly quiet, so it does the only thing it can. It flickers. It trembles around zero, never quite settling, jittering with a restless energy that has a name. We call it 0-point energy, the energy that remains when you have taken away everything that can possibly be taken away. Picture it through the pond again, because the image holds. Even with no pebbles falling, no wind, nothing disturbing it from outside, the surface of the quantum pond can never go truly flat. It shivers with tiny fluctuations, a permanent restless texture, the smallest possible level of motion that the rules will allow. There is no calm setting on the universe. The lowest the fields can go is not silence. It is a kind of perpetual quiet humming, present everywhere, in every cubic inch of so-called empty space, never stopping, never resting, since the beginning of time, and continuing long after you and I are gone. And there is a vivid way physicists picture this flickering, one that you have probably heard of and may be dismissed as a flight of fancy. The trembling of the fields can be described as pairs of particles popping into existence and then vanishing again almost instantly. A particle and its antiparticle, an electron and a positron, say, appearing out of the restless field, existing for the briefest sliver of time, and then annihilating back into the field they came from. These are called virtual particles, and they are constantly bubbling up and disappearing everywhere, in the box, in the room, in the space between the atoms of your body, in the gulfs between the stars. Empty space, looked at closely enough, is not a smooth nothing. It is a froth, a churn, a constant fizzing of particles, being born and dying faster than any clock could ever catch. I have to be careful here, because the phrase virtual particles makes a lot of people roll their eyes, and they are not entirely wrong to be cautious. These are not little balls you could ever catch in a net. You cannot reach into the vacuum and pull one out and put it in a jar. They live for too short a time, far less than the time it would take light to cross an atom, on the order of a billionth of a trillionth of a second or less. They are, in a sense, the mathematics of the field's flickering, the way we account for its restlessness. But here is the crucial thing, the thing that turns this from a fairy tale into hard physics. The flickering of the vacuum has consequences you can measure. The activity of empty space leaves fingerprints in the real world, fingerprints we can detect, weigh, and confirm. The vacuum's restlessness is not a story we tell. It is something the universe has signed its name to, again and again, in experiments we will look at in just a moment. Let me give you a sense of the sheer relentlessness of it, because the timescales are part of what makes it so strange to contemplate. These fluctuations are not occasional events that happen now and then in a quiet vacuum. They are happening continuously, everywhere, at a rate so fast that the word fast loses its meaning. In the time it takes you to blink, in the space of a single one of your heartbeats, an unthinkable number of these flickers have come and gone in every tiny region of the air in front of your face. If you could somehow slow time down and brighten the invisible, every cubic centimetre of the emptiest vacuum would look busier than any city at rush hour, a ceaseless storm of appearance and disappearance, of fields trembling at the lowest pitch the universe permits. Let me try to give you a more visceral feel for the energy that lives in this restlessness, because the numbers, while uncertain, are genuinely staggering. When physicists try to estimate how much zero-point energy is packed into empty space, they run into the problem that the answer depends on how small a scale you are willing to count down to, and the fields tremble at every scale, down to the very smallest. If you take the calculation at face value, all the way down, the energy in a single cup of empty space comes out to numbers so enormous they defy comparison with anything in ordinary life. Now, there are strong reasons to think this naive estimate is badly wrong, and we will come to that problem, the worst prediction in physics, later tonight. But the basic lesson stands. The emptiness is not a low-energy place, a quiet, resting state. By the natural reckoning of the theory, it is the most energetic thing there is, and the puzzle is not why it has energy, but why we see so little of that energy out in the world. I want to address a worry that may be forming, because it is a sensible one. If empty space is full of all this flickering activity, all these particles popping in and out, why does the world look so calm and solid and ordinary? Why does your bedroom not crackle and spark with this constant churn? The answer is that the activity is balanced, self-cancelling, almost perfectly quiet at the scales we can perceive. The particles that flicker into being annihilate again so quickly, and the fluctuations average out so smoothly over any time we could notice, that the net effect on everyday life is a gentle, invisible hum rather than a storm. It is like the surface of the sea seen from very high up, which looks like a smooth sheet of glass even though, up close, every inch of it is in violent motion. The vacuum is calm at our scale precisely because its restlessness is so fine-grained and so balanced. You live on the smooth, glassy surface of an ocean that is, underneath, never still for an instant. I find it helps to put this restlessness in human terms, because the abstractness can keep it at arm's length, and it deserves to feel close. Right now, in the few inches of air between your face and the pillow, the fields are flickering with this zero-point activity, the same as they have since the universe began. It does not stop when you sleep. It does not stop in the dark. It does not stop in the deepest cold of space between the galaxies, where there is not a single atom for light years in any direction, and yet the fields there are still trembling, still doing something, faithfully, endlessly. There has never been a single instant, anywhere in the history of existence, when the fields were truly at rest. The universe has been humming to itself, quietly, in every empty corner, the entire time. Tonight, you are simply learning to hear it. So here, finally, is the answer to the question in the title, stated plainly. What does the quantum field start doing once you finally understand it? It never stops. That is the answer. The instant you accept that there are no little balls, that reality is fields and particles are only ripples, you are forced to accept the rest of it too. There is no truly empty space, because the fields are everywhere, and the fields can never be perfectly still. The nothing you imagined is full. The darkness behind your eyes, the apparently empty air of your bedroom, the gulf between galaxies, all of it is humming with zero-point activity, a restless ocean that was never calm and never will be. The emptiness is the loudest proof of all that the world is made of fields. Because even when you take everything away, the field is still there, still trembling, still doing something. And the most remarkable part is that we did not have to take this on faith. We caught the vacuum in the act. Is less than break time equals 1s, is greater than... Part 7. How we know the emptiness is full. I told you the vacuum's restlessness leaves fingerprints, and I do not want you to take that on trust, so let me lay out the receipts, because this is where the strange idea becomes undeniable. The activity of empty space is invisible, far too fast and too faint to watch directly, but it pushes on the visible world in specific, measurable ways, and over the last several decades, physicists have measured them with great care. Each one is a place where the field's restlessness reaches out of the dark and leaves a mark we can read. Together they make it impossible to keep believing that empty space is nothing. The first fingerprint appeared in 1947, and it is called the Lamb shift. A physicist named Willis Lamb was studying the hydrogen atom, the simplest atom there is, a single electron around a single proton. According to the basic theory, two particular energy levels of that electron should be exactly equal, indistinguishable. But when Lamb measured them with great precision, he found they were not quite equal. There was a tiny difference, a small splitting where the theory said there should be none, and the explanation, worked out in the years that followed, was that the electron is not sitting in a quiet void. It is being constantly jostled by the fluctuations of the electromagnetic field, the restless flickering of the vacuum, and that jostling nudges its energy levels apart by just the amount Lamb measured. The vacuum had reached into a hydrogen atom and left a measurable mark. This was one of the first hard proofs that empty space is doing something. The second fingerprint is the one I find most beautiful, and it is called the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948. Imagine taking two flat metal plates, ordinary uncharged plates, and bringing them very, very close together in a vacuum, closer than the width of a human hair. Common sense says nothing should happen. There is no charge on them, no magnet, nothing between them but empty space. But quantum field theory makes a peculiar prediction. The restless fluctuations of the field fill all of space, vibrating at every possible wavelength. Out in the open, vibrations of all sizes can exist. But in the narrow gap between the two plates, only certain wavelengths fit, the ones that match the spacing, the way only certain notes resonate in a particular pipe. So there are fewer kinds of vibration allowed between the plates than outside them. And that imbalance, more restless activity pushing in from outside than pushing back from the gap, results in a net force. The two plates are pushed together by the vacuum itself. Let me make that force physical, because it is easy to hear Casimir effect and file it away as a tiny curiosity. The push is small when the plates are far apart, but it grows rapidly as they get closer. At separations of a fraction of a millionth of a meter, the pressure of the vacuum pushing those plates together can rival the pressure of the atmosphere, the weight of all the air above you pressing down. Think about that. The emptiness between two plates, the nothing, can shove as hard as the entire ocean of air over your head. And this is not a thought experiment. The Casimir force has been measured directly, many times with delicate instruments, and it comes out just as the theory of the restless vacuum predicts. Empty space pushes. We have felt it push. There is a third fingerprint, and this one you carry with you all the time, woven into the most ordinary glow of the world. Consider an atom whose electron has been kicked up into a higher energy state, an excited atom. Left alone, that electron will, after some time, drop back down to a lower state and spit out a photon, a flash of light. This is called spontaneous emission, and it is how almost everything that glows, glows. But here is the puzzle that the field picture solves. If you put that excited atom in a perfect vacuum, alone in the dark, with nothing around to disturb it, why does it ever decay at all? What tells the electron to drop down and release its light if there is nothing there? The answer is that there is something there. The atom is sitting in the electromagnetic field, and even in the dark, that field is fluctuating, trembling with its zero-point restlessness. Those fluctuations tickle the electron, nudge it, and eventually coax it into dropping down and emitting its photon. The light from a flame, the glow of heated metal, the warmth radiating off your own body right now, all of it is, at the lowest level, the restless vacuum drawing light out of matter. You are glowing faintly in the infrared, because the field will not leave your atoms perfectly alone. And the story is still being written, with new tools that would have seemed like magic to Lamb or Casimir. In the last couple of years, through 2024 and 2025, physicists have begun to simulate the behavior of quantum fields directly on quantum computers, using carefully arranged atoms and superconducting circuits to act out the mathematics of the fields. In some of these experiments they have watched, in a controlled system, the spontaneous creation of particle pairs out of a field, the very process we have been describing, played out where they can observe and measure it. We are no longer only inferring the restlessness of the vacuum from its side effects. We are beginning to build little laboratories where its behavior can be staged and studied on demand. I want to add one more receipt to the pile, because it connects the vacuum's restlessness to the largest structures in the universe, and it shows that this is not only a story about tiny laboratory effects. The leading idea for how the universe began its expansion, and how galaxies came to exist at all, leans directly on the restlessness of fields in the early cosmos. In the first instance after the beginning, according to the most widely held picture, the fields filling space were trembling with quantum fluctuations, just as they tremble now, but the universe was expanding so violently that those tiny flickers were stretched, frozen, and blown up to enormous size. Those stretched fluctuations became the slight unevenness in the early universe, the faint denser patches that, over billions of years, gravity pulled together into galaxies, stars, planets, and eventually us. If that picture is right, then the largest structures in existence, the great webs of galaxies stretching across the sky, are the grown-up descendants of the same vacuum flickering that jostles a hydrogen atom. The restlessness of empty space may be the seed from which everything we can see was grown. There is something I find quietly staggering in stacking all these effects together, and it is worth saying directly. The Lamb shift is measured in a single atom. The Casimir force is measured between two small plates. Spontaneous emission lights every flame and warms every body. And the fluctuations of the early universe may have sketched the map of every galaxy. All of these, from the smallest to the largest scale we know, are the same phenomenon, the same restless vacuum, the same fields refusing to be still. It is one behavior written across every size of the cosmos, from the inside of an atom to the span of the observable universe. Once you learn to see it, you cannot find a scale at which the field is doing nothing. There is no quiet corner anywhere, at any size, in all of reality. I want to draw out why the Casimir effect, in particular, ought to change how you feel about the word empty, because it is the place where the idea becomes almost tangible. When two plates are pushed together by nothing but the vacuum, you are watching empty space exert a real mechanical force, the kind you could in principle feel with your fingers if the scale were larger. It is not a subtle statistical whisper buried in decimal places. It is a push. Two objects move because of what the emptiness between them is doing. If someone had told you before tonight that you could place two plain metal plates close together in a perfect vacuum and they would drift toward each other on their own with no charge, no magnet, nothing between them, you would have been right to be skeptical. And yet it happens, exactly as the theory of the restless field predicts, measured again and again. The nothing pushes. Once you have absorbed that, the old idea of empty space as inert and lifeless simply cannot survive. So, let me gather all of this back to the single thread that runs through our whole night. We started with a question about what the field does once you understand it, and here is the answer made solid, stacked up out of measured facts. The Lamb shift, the Casimir force, spontaneous emission, the new quantum simulations, every one of them is a place where the activity of empty space reaches into the measurable world and leaves a mark we can read. The nothing is the most active thing we know of. That is not a poetic flourish. It is the plain conclusion of a century of careful experiment. Once you understand the field, you cannot point anywhere, not at the darkest corner of the emptiest box, and honestly say nothing is happening there. Something is always happening. The field is always doing something. And we are about to meet a field that takes this restlessness one step further. A field that is not merely flickering in the background, but is switched fully on, everywhere, all the time, holding the solidity of the entire universe in place. Is less than break time equals 1s? Is greater than? Part 8. The field that is switched on everywhere. We have spent the last while watching the fields flicker, trembling at the lowest pitch the universe allows, never quite settling into stillness. But all of those fields we have discussed so far share one feature. When left alone, they hover near zero, and they only spike up into something noticeable when a particle ripples through, when a real photon or a real electron comes along. The flickering is the background hum. The particles are the events that rise above it. But there is one field in nature that breaks this pattern completely, and once you understand it, it becomes perhaps the cleanest example in all of physics of a field that is unambiguously doing something, everywhere, right now, without rest. It is called the Higgs field, and it may be the strangest of them all. The Higgs field does not hover near zero in empty space. It sits at a non-zero value throughout all of the universe, in every cubic inch of it, even in the most perfect vacuum you could ever build. Take that box again, the one we emptied of every particle and cooled to absolute zero. The other fields inside it are flickering around zero, but the Higgs field inside that box is not flickering around zero. It is holding steady at a value well above zero, a constant, permanent presence filling the emptiness. It is, in the most literal sense, switched on. And the universe has been soaking in this switched-on Higgs field since a tiny fraction of a second after it began, when conditions cooled enough for the field to settle into its non-zero value and stay there. Why does that matter? It matters because that ever-present field is the reason most particles have mass at all. And mass, when you understand it through the field picture, is one of the most surprising ideas in physics, because it stops being a property that things simply have and becomes something that the field is doing to them. Let me build this up carefully, because it is worth getting right. In the world of fundamental particles, having mass is not automatic. There is no obvious reason a particle should be heavy rather than weightless. The photon, the ripple in the light field, has no mass at all, which is why it always travels at the full speed of light and can never slow down or rest. So the question physicists faced in the middle of the 20th century was not why some particles are heavy, It was why any of them are heavy. What gives a particle its mass, when the most natural state seems to be having none? The answer, proposed in the 1960s by Peter Higgs, and independently by Robert Brout and François Englert and a few others working along similar lines, is that particles acquire mass by interacting with the ever-present Higgs field. Picture it this way, and I will be honest that this is a rough picture rather than the exact mathematics, but it captures the spirit. The Higgs field fills all of space, and as a particle moves through it, the particle interacts with the field, and that interaction acts like a kind of drag, a resistance, a sluggishness. Particles that interact strongly with the Higgs field feel a lot of this drag, and we experience that drag as them being heavy, hard to push, slow to get moving. Particles that interact weakly feel only a little drag and are light. And particles that do not interact with the Higgs field at all, like the photon, feel no drag whatsoever and remain massless, racing along at the cosmic speed limit forever. I want to be careful with the drag metaphor because it can mislead if you push it too far. It is not that the Higgs field slows a moving particle down the way honey slows a moving spoon, draining its speed until it stops. A particle with mass, once moving, keeps moving. The resistance is more subtle than that, a resistance to changes in motion rather than to motion itself, which is exactly what physicists mean by mass, by inertia. The cleaner way to say it is this: mass is a measure of how strongly a particle is coupled to the always present Higgs field. The more strongly it grips that field, the more mass it has. Your weight, the heft of your body, the resistance you feel when you try to shove a heavy object across the floor, all of it traces back, at the most fundamental level, to how the particles you are made of interact with a field that fills the empty space around you and never switches off. Now let me connect this back to the idea we built in the second act, the idea of one field per kind of particle, because the Higgs field obeys that same beautiful logic, and it is what allowed us to confirm that it is really there. Remember that every field has its ripples, its particles. The light field has the photon, the electron field has the electron. So the Higgs field, if it is real, should also have a ripple, a particle of its own, a quantum of disturbance in the Higgs field. That particle is called the Higgs boson. And here was the great test. If the Higgs field is truly filling all of space, then we should be able to find its particle, to knock a ripple out of the field and detect it. The trouble was that the Higgs boson is heavy, much heavier than ordinary particles, and so creating one requires concentrating an enormous amount of energy into a tiny space, more than any machine on Earth could manage for decades. That is a large part of why the Large Hadron Collider was built, the giant ring of magnets buried beneath the border of France and Switzerland, the most complex machine humanity has ever constructed. It smashes protons together at nearly the speed of light, concentrating energy into points small enough and intense enough to occasionally shake a ripple loose from the Higgs field. And in 2012, after a long search, the teams at the Collider announced that they had found it. They had detected the Higgs boson, the particle that is to the Higgs field, what the photon is to the light field, the proof that the field is genuinely there, filling all of space, switched on everywhere. It was one of the great confirmations in the history of science, the discovery of the field that gives the universe its mass, and the work has not stopped. Through the current run of the Collider, continuing through 2025, physicists keep measuring exactly how strongly the Higgs field couples to each kind of particle, testing whether the heavy particles really do grip it as firmly as the theory says, refining the picture of how mass is handed out across all of matter. So, let me draw the line straight back to the thread of our whole night, because the Higgs field is, in a way, the purest illustration of everything we have been building toward. We started by saying that reality is not made of little balls, but of fields, and that those fields are never truly still, that even empty space is doing something. The flickering vacuum we met in the last two parts is one face of that restlessness, a trembling, a background hum that proves the fields are always active. But the Higgs field is a different and even more direct kind of doing. It is not merely flickering in the background. It is holding steady at a non-zero value, everywhere, continuously, and that steady presence is actively building the mass of the universe, every moment, in every particle. When you feel the solidity of the floor, the weight of your own limbs, the heft of the world around you, you are feeling a field at work. The solidity you once attributed to little balls of stuff is, in truth, the Higgs field doing something to the ripples that make you up, without ever resting, without ever switching off. There is a way to feel just how strange this is. Most of the mass you think of, the mass of the protons and neutrons in your body, actually comes from the energy of the fields binding the quarks together inside them, which is its own remarkable story. But the mass of the fundamental particles themselves, the mass of the electron, the masses of the quarks, the heaviness of the particles that carry the weak force, all of that traces to the Higgs field. Without the Higgs field switched on, the electron would be massless, and massless electrons would race around at the speed of light, unable to settle into orbits, unable to form atoms. There would be no atoms, no chemistry, no molecules, no structures, no you. The fact that there is a stable world at all, a world where things can hold together and stay put, depends on a field that fills the empty space and never turns off. Empty space, the nothing we keep returning to, is quietly responsible for the existence of everything solid. I find it worth pausing on that inversion, because it overturns the deepest assumption of the old picture. In the marble universe, empty space is the inert backdrop, and the particles are where all the action is, all the substance, all the importance. In the field universe, it flips. The empty space is where the most important things are happening. The vacuum's flicker shapes the precise behavior of every particle. The Higgs field's steady presence in the vacuum gives every particle its mass. The nothing is not the absence of the action. The nothing is the source of it. Once you understand the field, you stop seeing emptiness as the boring part of the universe and start seeing it as the engine room. There is one more thread to pull here, and I will only touch it for now because it sets up something we will face near the end of our night. The value that the Higgs field settles at, the non-zero level it holds throughout space, is a particular number, and physicists have wondered whether it is the lowest possible value the field could have, the most stable resting place, or whether it is merely a comfortable valley that happens not to be the deepest one available. That might sound like an abstract worry, a detail for specialists. But if the Higgs field is sitting in a valley that is not truly the bottom, then in principle, somewhere, sometime, it could find its way to a lower one, and the consequences of that would be more dramatic than almost anything else in physics. We will come back to that unsettling possibility. For now, hold on to the central image. There is a field filling all of empty space, switched fully on, and its constant restless activity is what builds the solidity of the world. The nothing is doing the most important work of all. Let me slow down on the idea that mass is something the field does, rather than something a particle simply has, because it overturns one of the most basic assumptions you carry, and it deserves a proper unfolding. When you step on a scale in the morning, you think of your weight as a fixed property of the stuff you are made of, an amount of substance that is just there, intrinsic, yours. But the field picture says something subtler and stranger. The mass of the fundamental particles in your body is not a lump of substance they contain. It is a measure of a relationship, an ongoing interaction between each particle and the Higgs field filling the space it sits in. Take away the Higgs field, switch it off, and those particles would not become lighter versions of themselves. They would become massless, racing at the speed of light, unable to slow down, unable to be the building blocks of anything stable. Your mass is not a thing you own. It is a thing that is being done to you, continuously, by a field you cannot see, in space that looks empty. I find it helps to compare the two kinds of field activity we have now met, because together they complete the picture of a universe that is never doing nothing. The vacuum fluctuations we spent the last two parts on are a restless, flickering, trembling kind of activity, an unceasing jitter that averages out to a quiet hum. The Higgs field is a different kind of activity altogether. It is not flickering. It is steady, constant, a field holding firm at a non-zero value everywhere, like a tone held without pause. One is the universe trembling. The other is the universe humming a single, unbroken note. But both are the field doing something in the so-called emptiness, and both are essential to the world existing at all. Between the trembling vacuum and the steady Higgs, there is no moment and no place where the fields fall silent. The emptiness is busy in two completely different ways at once, all the time, everywhere. There is a beautiful subtlety in how the Higgs field came to have its value, and it tells you something about the universe's history. In the first tiny fraction of a second after the beginning, the universe was so hot that the Higgs field was, in effect, switched off, sitting at zero like the other fields, and in that searing early moment, the fundamental particles were massless, all racing at light speed in a kind of undifferentiated symmetry. Then, as the universe expanded and cooled past a certain point, the Higgs field underwent a change, almost like water freezing into ice, settling out of zero and into its non-zero value, switching on across all of space. And in that instant, particles that interacted with it gained their masses. The perfect early symmetry was broken, and the world of distinct, heavy, structure-forming particles became possible. The mass of everything you are made of was switched on once, very long ago, when the cosmos cooled enough for a field to settle. You are living inside the frozen state of a field that crystallized in the first moment of time. I want to make one more connection, because it brings the Higgs back to the very precision we marveled at earlier. Remember the muon, the heavy cousin of the electron, whose wobble we can measure to a part in a billion. The reason the muon is heavier than the electron, the reason it has more mass to begin with, is that it grips the Higgs field more strongly than the electron does. The whole hierarchy of particle masses, why some particles are featherweight and others are heavy, is a map of how firmly each one holds onto the ever-present Higgs field. So when physicists measure these masses with great care at the collider, they are, in effect, measuring the strength of each particle's grip on a field that fills the empty vacuum. Every mass in the table of particles is a number that describes a conversation between a ripple and the switched-on field around it. There is nothing in that table that is not, at bottom, the Higgs field doing something. And once again, the place where all this happens, the place that holds the field and hands out the mass, is the emptiness we keep being told is nothing. When physicists started to ask what happens when these fields meet the strongest force of all, gravity, and what happens to the very idea of a particle near something as extreme as a black hole, they found that the field, the thing we have been treating as the bedrock of reality all night, holds firm even when our most basic notions begin to dissolve. Because the next twist is a strange one. It turns out that even the question of how many particles are present, a question you would think has a definite answer, stops having one. So what happens to a particle when the field that carries it falls under the influence of gravity, and who gets to say how many particles there really are? Is less than break time equals 1s is greater than, part 9, when fields meet gravity, even how many particles stops being real. All night we have been speaking as though one fact about the world were obviously fixed, even while everything else dissolved. We let the marble go, we accepted that particles are ripples, but we kept assuming that at least you can always count them, that the number of particles present in a region is a definite, agreed-upon fact. It turns out that even this dissolves once fields meet gravity and acceleration. The bedrock of the count gives way, and the only thing left standing underneath is the field itself. Consider first something called the Unruh effect, a prediction that follows from combining quantum field theory with the physics of acceleration. Imagine you are floating in the emptiest vacuum, perfectly still, and you measure the space around you. You find it cold and empty, no particles, the quiet, flickering vacuum we have described. Now imagine a second observer who is not still but accelerating, racing faster and faster through that same vacuum. According to the theory, that accelerating observer would not find empty cold space. They would find themselves immersed in a warm bath of particles, a faint glow of real warmth, where you, hovering still beside them, detect nothing at all. The same patch of vacuum contains no particles for one observer and a sea of them for another. The number of particles present depends on how you are moving through the field. The most famous version of this strangeness happens at the edge of a black hole, and it is Stephen Hawking's great discovery. Near the horizon of a black hole, the boundary past which nothing returns, the restless fluctuations of the vacuum get split apart by the extreme gravity. The pairs of virtual particles that normally flicker into being and annihilate harmlessly can instead be separated, one falling in past the horizon, the other escaping outward as a real particle. To a distant observer, the black hole appears to glow, faintly, with what we now call Hawking radiation, and over unimaginable spans of time it slowly evaporates, giving up its mass to particles born from the field at the edge of nothing. The vacuum, cut by a horizon, produces real light. It is worth sitting with how unsettling this really is, because it cuts against something we almost never question. We are used to the idea that different observers might disagree about colours or speeds, or even, thanks to Einstein, about the timing of events. But the number of particles in a region feels like it should be a hard, countable fact, the kind of thing everyone must agree on, like how many chairs are in a room. Quantum field theory says no. Whether a given patch of vacuum is empty or full of warmth can depend on whether you are standing still or accelerating through it. The particle is revealed to be a kind of perspective, a way of carving up the field that depends on the carver. What is not a matter of perspective, what every observer shares, is the field underneath. The field is the common ground beneath all the disagreements. This connects to one of the most profound results in modern physics, the slow evaporation of black holes, and it is worth seeing why it matters so much. For a long time, black holes were thought to be perfectly black, perfectly final, places where things fell in and nothing ever came out. Hawking's discovery, born from taking the quantum field seriously near a horizon, was that black holes are not truly black at all. They glow faintly, and over time spans far longer than the current age of the universe, they would slowly shrink and disappear, returning their substance to the cosmos as a thin radiance drawn from the restless vacuum at their edge. The most absolute boundary in nature turns out to leak, because the fields are doing something even there, at the rim of where space and time themselves break down. So here is the twist gathered to our thread, and it may be the cleanest proof of the whole picture. The number of particles in a region is not an absolute fact. It depends on the observer, on their motion, on the gravity around them. But underneath every one of those disagreeing observers, the field is still there, the same field doing what it does. The particle count is a description, an approximation that works well in calm, flat space and falls apart in extreme conditions. The field is what stays real when even particle counting fails, and that is the strongest sign we have met all night that fields, not particles, are the true bedrock of reality. The thing that survives when everything else becomes a matter of perspective is the field, never still, always there. Is less than break time equals 1s, is greater than. Part 10. the fields might be sitting in the wrong valley. I promised earlier that we would return to the boldest version of the idea that the field is always doing something, and here it is, the possibility that the very emptiness we live inside is not as settled as it looks. This is speculation, and I will flag it clearly as we go, but it is speculation that serious physicists take seriously, and it grows directly out of everything we have built tonight. Remember the Higgs field, switched on throughout all of space, resting at its particular non-zero value. We asked whether that value is the deepest possible valley, the most stable resting place, or merely a comfortable ledge that is not truly the bottom. If it is only a ledge, then the vacuum we inhabit is what physicists call a false vacuum, a state that looks stable but could, in principle, find its way to a lower one. And if a tiny region of space ever did slip down to that lower, truer vacuum, it would form a bubble. And that bubble would expand outward at nearly the speed of light. And inside it, the laws of physics would be subtly rewritten. I want to be very clear, because this is the kind of idea that can sound alarming. The calculations suggest that if this can happen at all, it is astronomically unlikely on any timescale that matters to you, to humanity, to the Earth, to the Sunday. This is not a thing to lose sleep over. It is a thing to find wonder in, a reminder that even the stability of the vacuum is, at bottom, a question about what the fields are doing and whether they have truly come to rest. There is a second, quieter version of this puzzle, and it is one of the great unsolved problems in all of physics. When you try to calculate the energy of the restless vacuum, all that zero-point flickering we have been describing, the naive estimate from quantum field theory comes out enormous. But when astronomers measure the actual energy of empty space, by watching how the expansion of the universe is speeding up, driven by what we call dark energy, the value they find is fantastically smaller. The mismatch between the predicted vacuum energy and the observed dark energy can be as large as a factor of 10, followed by 120 zeros. It is, by a wide margin, the worst prediction in the history of science, a disagreement so enormous that it tells us something fundamental is missing from our understanding. And it is, at its core, a question about what the vacuum is doing. Recent surveys, including results from 2024 and 2025, have even begun to hint that dark energy might not be perfectly constant, deepening the mystery rather than resolving it, though whether it is truly linked to the vacuum's energy remains unproven. So we end this part, where we have circled all night, at the nothing that refuses to be silent. The biggest unsolved number in physics, the most dramatic and the most embarrassing gap between what we predict and what we see, is a question about the energy of empty space. The same emptiness we started with, the supposed nothing, turns out to hold the deepest mystery we have. The field is doing something in the vacuum, something so large or so strange that our best theory misjudges it by more than any other quantity we have ever tried to compute. We do not yet know the answer, but notice that the question itself only makes sense once you have understood the field. Only then can you even ask what nothing weighs. Is less than break time equals 1s, is greater than part 11. Settle into a universe with no empty space. Let us gather the whole night together now, slowly, the way you would gather a blanket up around your shoulders before sleep. We began with a little ball, the marble you were handed as a child, the picture of matter as tiny solid objects packed into a void. And we let it go, piece by piece. We followed Faraday's iron filings to the first idea of a field, and Maxwell's equations to the discovery that light is a ripple in one. We watched the photon fall out of the quantized field in the 1920s, the particle revealed as a vibration of something deeper. We met the one electron field that explains why every electron in the universe is identical, and we faced the strange truth that the electron has no size, that it is a point, a ripple with no marble underneath. We saw Dirac conjure antimatter from a single equation, and we stood on the most precise prediction humans have ever made, the electron's magnetism agreeing with reality to a part in a trillion. And then we arrived at the answer to the question I asked at the very start. What does the quantum field start doing once you finally understand it? The answer is that it never stops. It is never still, never silent, never empty. It ripples into the particles that make up everything you can touch. It hums beneath the darkest, coldest, emptiest space with a 0-point restlessness that can never be removed. It pushes two plates together across a gap of nothing. It draws light out of a lonely atom in the dark. It holds steady in the Higgs field, switched on everywhere, building the mass of the world. It glows at the edge of black holes, and it carries the deepest unsolved mystery we have in the energy of the vacuum. Wherever you point, in the fullest star or the emptiest void, the field is doing something. So, let me offer you a new picture to fall asleep inside, to replace the old one. You are not a clump of tiny marbles arranged in the shape of a person, sitting in an empty room. You are a set of standing patterns, ripples held in a handful of fields that fill the entire universe, a temporary and rather beautiful arrangement of vibrations that has cohered for a while into you. The space around you is not empty, and the space inside you is not empty. The gap between your hand and this blanket, the air of the room, the dark behind your eyes, all of it is full of the very same fields you yourself are made of. There is no real boundary between you and the apparent emptiness around you, because you and the emptiness are made of the same restless stuff, the same fields, never quite at rest. I find something genuinely calming in that, and I hope you do too. The separateness you usually feel, the sense of being a small solid thing alone in a great empty space, softens once you understand the field. You are not a lonely object in a void. You are a pattern in a continuous medium that stretches unbroken to the farthest galaxies. The same fields that hum in the space between the stars hum in the space between your atoms. You are woven into the fabric, not dropped into the gap. It is worth saying plainly that this new picture does not make you less real or less solid. Sometimes when people first hear that they are mostly fields and almost no stuff, that the solid floor is a negotiation between ripples, they feel a little unmoored, as though the world had been revealed to be thin or illusory. I want to gently push against that feeling because it gets the lesson backward. You are not less real for being made of fields. The fields are the most real things there are, the bedrock that survives even when particles become a matter of perspective. The solidity of the floor is no less trustworthy for being a conversation between electron fields, because that conversation is utterly reliable, holding the world together every moment without fail. Understanding what underlies the solidity does not dissolve it. It deepens your appreciation of how something so steady and dependable is built from something so restless and alive. You are real, and you are made of the realest stuff in existence, and that stuff happens to be a set of fields that never stop singing. There is much we still do not know, and I want to leave that with you not as a worry, but as a kind of comfort. We do not know the true energy of the vacuum. We are not certain whether the muon's faint wobble hides a field we have not yet discovered. We do not know with full confidence whether the fields themselves are the final bottom layer of reality, or whether something even more basic underlies them. The picture is not finished, but there is a peace in that openness, the peace of knowing that the universe still has secrets to give, that the people who study these fields will wake tomorrow and keep listening, and that the answers, when they come, will almost certainly be stranger and lovelier than anything we expect. Let me hand the journey back to you in the simplest terms I can, the way you might repeat a single clear thought to yourself as you drift off. The world is not made of things. It is made of fields. The things are what the fields are doing. And the fields are doing something always, in the brightest star and in the emptiest dark, in your body and in the space around it, in the first instant of the universe, and in this quiet moment, before sleep, the little ball you were handed as a child was a kindly simplification, a stepping stone, and it served its purpose. But the truer picture, the one the experiments keep confirming to a part in a trillion, is gentler and grander at the same time. You belong to a continuous, restless, unbroken medium that fills all of existence, and you are one of the lovely temporary shapes it has learned to make. So as you lie there now, let me leave you with the plain truth of where you are. The room around you looks empty, but it is not. Every cubic inch of the dark air above your bed is humming with the restless activity of fields that have never once been still, not in the whole history of the universe. You are drifting off to sleep inside the loudest nothing there is, cradled in a vacuum that is fuller than any crowd, made of the same vibrations that fill the spaces between worlds. The universe never goes quiet, and neither, quite, does the nothing inside it. And there is, I think, no gentler thing to fall asleep to than the steady, endless hum of a field that will keep on doing something, everywhere, all night, long after you have closed your eyes.